Hello, my name is Grant Wallace, and this is an explanation of the holographic principle. Now, throughout time, humans have looked at things and they've wondered, why does that happen? And this is what we'd call science, that is making theories and making hypotheses and explanations for why things happen in the world. But when we see things that we don't yet understand, but we have two contradicting viewpoints of how they work, we run into what we call a paradox. And in physics, we run into these paradoxes quite a bit. Be it in wave-particle duality, the idea that a particle of light can be both a particle and a wave, or through Einstein and his theories of general relativity and space-time and things like that, or with Boseman and his ideas of quantum mechanics and the inevitable line of time. We run into these paradoxes that occur, and we have two sets of understandings that occur, and they're both right, I guess you could say, according to what some people would say, but they run into one particular point or one particular peak of understanding where they make no sense, and where neither of them are necessarily correct, or both are correct. Now recently, a scientist by the name of Leonard Susskind and another physicist by the name of Stephen Hawking, as we all know and love, they ran into a disagreement, and it was about black holes, and more particularly what happens when you enter a black hole, from two observers' points of views. Now, let's take one observer A, I guess you could say. Let's name this observer Alice, A for Alice, and Alice decides to go into the black hole, and Alice walks right on through the event horizon, the point where light can no longer escape the center of the black hole. Or not even rather the center, but it cannot escape the black hole or from that point, the event horizon. And Alice walks through that event horizon and is pulled apart by the forces of gravity after the event horizon. But that's what Alice sees. And another observer, observer B, or we'll call him Bob, observer B sees Alice walk to this event horizon, but Bob can't see past that event horizon because light can't escape from there. So what does Bob see? Well, from Einstein's theories of general relativity, we know that as you approach the center of a black hole, time begins to slow down and begins to stop. So he'd see Alice approach this event horizon. It gets slower and slower and slower, but she's still moving. And she'd get to the point where she's gradually being shortened and compressed, and I guess you could say squeezed and stretched out, and stretched and molded in a way, sort of like onto the surface of this black hole. And she becomes thinner than the basic elementary particle or building block of the universe and of matter within our universe called a quark. And she begins, as some physicists theorize, a string, a 9-dimensional string. That's another thing from string theory. They say that the basic compounds of reality are these strings that vibrate and make all matter that we know. And she'd become these strings, and she'd become projected onto the surface of this black hole. So now what we know about black holes is that when you put in one, I guess you could say, digit of information, like say a photon or a piece of light, with the smallest amount of information that you can really have a photon hold into a black hole, the black hole event horizon, and actually the black hole itself, increases in size by 1 bit or unit of area. The smallest unit of area, which we call a Planck area, or a Planck space area. So if we put 1 bit of information into the black hole, we get a proportional amount of increase in the surface area of the black hole. Now, this leads to the idea that the black hole holds the same amount of information that the surface area contains. So as Alice approaches this black hole and gets sort of squeezed into the basic strings of reality, she gets projected onto the surface of this black hole, and the black hole increases in surface area to match her information that we put into the black hole. So she's projected onto the surface of this black hole, and she becomes decoded, almost like a hologram. If you look at what really a hologram is, it's just basic information coded within one small amount or degree of freedom, as some physicists say, the amount of knowledge we know of whether a particle can move in one direction or another, or the position of something. We decode the information of what Alice is down to 1 degree of freedom. She's made into these strings that are molded, or I guess you could say projected, onto the surface of this black hole, almost like a hologram. Now she begins to stay there, and the energy increases of the surface of the black hole, and the temperature increases with that energy level, and there's a bunch of other things that happen with the surface of this black hole, and whether she dies by spaghettification or by the stretching of the gravity or by the burning up of the temperature around the black hole. We don't really know Alice's fate 100%, but the interesting part and the most important part is the idea that as Alice approaches that black hole, from another observer's point of view, we see her projected and molded onto the surface of this black hole. Now, a couple years later, or rather, I think a decade later, another physicist decided that he would look into this, and he thought about what makes a black hole a lot like our universe. A black hole has mass within it, it has energy within it, and it has a horizon. Just like our universe, a black hole has a horizon, a point where light can't escape and you can't see into it, no one can see out of it. So our universe has a boundary, and I guess you could say it's nondescript, but it does have a boundary to it. And we can't see out of it, and nothing can see necessarily into the black hole, well, not into the black hole, but into our universe. So these two very common and self-evident properties of our universe and properties of black holes hold very interesting parallels, meaning that maybe the information that's all within our universe and the location of every single particle and the galaxies that exist and are created by those particles and are formed by those particles, and even the information of how much hairs you have on your head could be coded, very scrambledly coded, but coded on the surface of our universe, the surface of the boundary of our universe, because it's all proportional. The surface area of our universe, I guess you could say, is proportional to the amount of locations, the amount of information, the amount of degrees of freedom, and the amount of entropy that's all within our universe. And they're all proportional. It's just a matter of how scattered the information is. It's all within the holographic, two-dimensional paper, I guess you could say, or fabric, the two-dimensional fabric of reality that exists within our reality. Now, the only issue with having this two-dimensional scattered information is that we don't know how to access it. But that's an entirely different story. The most important part about this whole paradox that occurred, the most important part about this theory, or rather principle that's being used in physics now, lately, with string theory, M theory, and all these other theories to describe our universe, we're using bits and pieces of the holographic principle, the theory that the hologram of the two-dimensional surface of our universe describes what's within it. So we're using this currently, and we've been using it for a couple of years now, and it's a very interesting discovery that led from a paradox and kind of relates to the whole history of physics and the underlying story of paradoxes lead to jumps in understanding and in knowledge. So what does this all really mean? Well, we've seen that science runs into paradoxes, and from these paradoxes we get the true reality of what happens to our world and what happens in our world when we interact with it, and the very interesting kind of abstract things that do occur help us with our day-to-day basic lives and help further science. We know that Stephen Hawking was wrong when he thought that information could be destroyed, and Susskind was right, and it's actually projected onto the surface of a black hole, and that the differences between viewers and how they interact with each other and with other matter, especially black holes and these event horizons, are completely different. And from there, we've understood that the projection on to the black hole of Alice, seen by Bob, leads to an increase in surface area and an increase in mass and volume of that black hole in the event horizon. From there, we also know that we can relate black holes to our overall universe. We can relate the very fact that information is coded and placed onto the surface area of a black hole to the universe, that it's coded and placed onto the surface of our universe, and it describes every individual bit of information, just maybe not in a way that we can fully understand. So to kind of put it into a couple words, black holes have helped us understand reality because of this holographic principle. We understand that the complex coding of reality of these two-dimensional surface areas can completely revolutionize how we feel about theories like string theory and M theory, and universal or unified field theory, and all of these other complex things that we're dealing with in mathematics and theoretical physics to this date.